This paper titled, Carbon Nanotube Composites with Bottlebrush Elastomers for Compliant Electrodes, discusses the development of a new class of supersoft, conductive composites for use in wearable electronics and biointerfacing technology. These materials are designed to be both compliant and conductive, making them suitable for applications that require materials with these properties, such as monitoring physiological signals, electronic skin, and body motion tracking. The typical design strategy for such materials involves polymer composites containing conductive particles. However, the addition of a hard filler often leads to an increase in stiffness that is not compatible with biological tissue. To address this challenge, the authors propose using Bottlebrush polymer networks as the matrix for the composites. These networks are known to be several orders of magnitude softer than comparable linear networks due to their unique architecture, which suppresses entanglements. In this study, the researchers embedded carbon nanotubes, CNTs, in Bottlebrush polymer networks to create conductive composites. The CNTs were chosen as the conductive filler due to their flexibility and high aspect ratio, which enable percolation at lower loadings than spherical particles. The addition of CNTs resulted in composites with shear moduli ranging from 66 to 140 kPa, which are significantly softer than composites containing linear polymers. The conductivity of the composites was in the range of 10⁻² to 10⁻⁻1 s per meter. One of the advantages of the Bottlebrush matrix chemistry is the presence of dynamic polyester bonds, which facilitate thermal reprocessing. This means that the materials can be heated and reformed without losing their mechanical integrity. This reprocessing ability is important for sustainable device design and provides opportunities to tailor the structure and properties of the composites. Overall, this study presents a new materials platform for conductive composites that combine softness, conductivity, and reprocessability. The use of Bottlebrush polymer networks as the matrix for these composites offers new opportunities for the development of advanced materials for wearable electronics and biointerfacing applications. Schematic representation of Bottlebrush polymer network formation. Note the Bottlebrush polymer sidechains are capable of reinitiation and complete incorporation of the monomer, which results in an all-solid material after cross-linking. Chemical structures of the various resin components and the resulting Bottlebrush polymer network. In this figure, the authors present a schematic representation of the Bottlebrush polymer network formation process. The Bottlebrush polymer sidechains are capable of reinitiation and complete incorporation of the monomer, resulting in an all-solid material after cross-linking. The chemical structures of the various resin components and the resulting Bottlebrush polymer network are also shown. This figure is significant because it provides an overview of the synthesis and structure of the Bottlebrush polymer composites. It helps to understand the unique architecture of the Bottlebrush polymer networks and how they contribute to the mechanical and electrical properties of the composites. This information is crucial for interpreting the results presented in subsequent figures. Rheological characterization of neat Bottlebrush networks, no added CNTs, starting from a 170 kDa Bottlebrush precursor, NBB equals 85, NSC equals 15. In situ curing of various Bottlebrush polymer resins truncated to highlight the region of interest. For full traces, refer to figure S5. Frequency-dependent modulus data capturing the room temperature rubbery plateau. This figure presents the rheological characterization of neat Bottlebrush networks without any added carbon nanotubes, CNTs. The in situ curing of various Bottlebrush polymer resins is shown, highlighting the rapid increase and plateauing of the storage, G, and loss, G, moduli, indicating robust network formation. Frequency-dependent modulus data is also shown, capturing the room temperature rubbery plateau. The results from this figure demonstrate the successful formation of Bottlebrush polymer networks with desired mechanical properties. The rapid increase and plateauing of the moduli indicate efficient cross-linking and formation of a strong network structure. The frequency-dependent modulus data confirms the rubbery plateau behavior of the Bottlebrush networks, which is desirable for applications requiring compliant and elastic materials. Photographs of two thin films with 0% and 0.1% WTCNTs after mechanical mixing. Optical micrographs confirm the efficient dispersion of CNTs in P4MCl Bottlebrush polymers. In this figure, Photographs of two thin films with different weight percentages of carbon nanotubes, CNTs, after mechanical mixing are shown. Optical micrographs confirm the efficient dispersion of CNTs in the P4MCl Bottlebrush polymers. The results from this figure demonstrate the successful dispersion of CNTs in the Bottlebrush polymer matrix. The photographs and optical micrographs provide visual evidence of the homogeneous distribution of CNTs throughout the polymer matrix. This is critical for achieving the desired electrical and mechanical properties of the composites. Bottlebrush CNT composites cure rapidly at 180 degrees Celsius starting from a 150 kDa Bottlebrush precursor, NBB equals 88, NSC equals 12. Room temperature frequency sweeps after curing show a soft rubbery plateau. In this figure, the curing behavior of Bottlebrush CNT composites is shown. The composites cure rapidly at 180 degrees Celsius, as evidenced by the increase in storage, G, and loss, G, moduli. Room temperature frequency sweeps after curing show a soft rubbery plateau. The results from this figure demonstrate the successful incorporation of CNTs into the Bottlebrush polymer matrix and the formation of a cured composite material. The soft rubbery plateau observed in the frequency sweeps confirms the compliance and elasticity of the composites, which is desirable for applications requiring compliant electrodes. Conductivity of the 0% and 0.1% WT-CNT composite samples measured in the frequency range of 0 Hz to 100 kHz, 100 mV AC amplitude, no bias. Photographs of the 0.1% WT-CNT sample used as a resistor to modulate the current in an LED circuit. In this figure, the conductivity of the Bottlebrush CNT composite samples is measured in a wide frequency range. The samples exhibit stable conductivity with frequency-independent resistance and in-phase current and voltage, typical of ideal resistors. The conductivity values are shown for different weight percentages of CNTs. Additionally, photographs show the Bottlebrush CNT composite used as a resistor to modulate the current in an LED circuit. The results from this figure demonstrate the electrical conductivity of the Bottlebrush CNT composites. The stable conductivity across a wide frequency range indicates the efficient percolation of CNTs in the polymer matrix. The photographs show the practical functionality of the composites as resistors in an LED circuit, highlighting their potential for use in electronic applications. Dynamic mechanical thermal analysis showing partial recovery of the tensile modulus, measured on cooling at 5 degrees Celsius per minute. Optical microscopy of pristine and reprocessed samples. The scale bars are 1 mm. Pictures taken throughout the process. In this figure, the reprocessing behavior of the Bottlebrush CNT composites is shown. Dynamic mechanical thermal analysis reveals the partial recovery of the tensile modulus after reprocessing. Optical microscopy images show the pristine and reprocessed samples, highlighting the changes in surface roughness. Additionally, pictures taken throughout the reprocessing process are shown. The results from this figure demonstrate the dynamic and reprocessable nature of the Bottlebrush CNT composites. The partial recovery of the tensile modulus after reprocessing indicates the ability to modify and tailor the mechanical properties of the composites. The optical microscopy images provide a visual representation of the changes in surface roughness, further confirming the reprocessable nature of the composites. The paper discusses the development of a new class of conductive composites comprising carbon nanotubes, CNT, embedded in Bottlebrush polymer networks. The Bottlebrush architecture of the polymers allows for the creation of materials that are several orders of magnitude softer than comparable composites with linear polymer networks. The composites maintain a low shear modulus while achieving a typical conductivity for CNT composites. The presence of dynamic polyester bonds in the Bottlebrush matrix chemistry enables thermal reprocessing of the materials without loss of mechanical integrity. The authors demonstrate the feasibility of using these composites as compliant electrodes for wearable electronics and biointerfacing technology. The results highlight the potential of highly branched polymer architectures in the design of soft and conductive materials with tailored properties. If you are an author or copyright holder for the work presented in this video and you have any issue with the existence or contents of this video, please let me know.